Good. So this is, yeah, as Lionel said, it's quite a different, it's a little bit of a different perspective, coming more from this, of course, at this twistor side. And this is a bit of an old work of mine with David and Tim for the gravity case, and then with Tim for the H theory case. So this is the gravity, and this is the one in the H theories. And if you're familiar with these twistor strings constructions, you're going to see that these two models, which are going to be written in terms of null infinity, scry, as it's called, are very similar to these models. So these two are scry models. And there is also relevant work done by Lionel and collaborators on the slightly different space, on ambitwistor space, which has relationships to scry, but I'm not going to go into details. But there is also a nice story here, and I can talk about it if people ask later about it. But my main focus is going to be really on scry. Okay. So, and I'm going to approach it also from the point of view of scattering, right? So, but it's slightly different. So what is scry? Well, as we seen this morning, if I draw the compactified, the Penrose diagram for Minkowski space, then I have two regions that I'm more interested in now, which are going to be the future null infinity, which is called scry plus, and the past null infinity, which is called scry minus. Okay, and why might you think these are relevant for scattering? Well, if you think about null scattering massless particles, you can think about all of the null data is given in terms of data on scry minus. All the in data is given in terms of external data in scry minus, that you propagate using Feynman diagrams into the bulk. Then there are some interactions that happen in the bulk, and then things propagate out, assuming everything is massless, of course, to scry plus. Right? So you might think that scry minus and scry plus are really kinematical, play a kinematical role. This is the role of the in state, and here in scry plus, the role of the out states, while the S matrix, which gives you your amplitude when you get out S matrix and in, is somehow here in the bulk, right? But I'm gonna show you how these models actually compute the three-level S matrix by only knowing data, radiative data on scry minus and scry plus, or more specifically in the complexification of scry. Okay. So why would you want to have a description like that, where you only talk about scry and not the bulk? Well, two things. One of them, which was inspiration for the paper, is that you can pick this twistor string formulas and play around with them, and that's what Freddie has done in one of the papers. And you find expressions that seems to want to live on only the null boundary. So you might imagine that, well, then there should be some way of computing that just from this data. The other is that there's been quite some interest on the symmetry group of scry. It's, well, renewed interest, I should say, because this is an actual quite old subject. So symmetry group of scry, which is called the BMS group, or Bondi, Metzner, and Sachs. There are other ways of defining a symmetry group, but this seems quite natural from the perspective of symptotically flat spacetimes. And what's interesting is that this group is actually infinite dimensional. So I'm going to come back and talk a bit more about it in a second. So you might imagine, can we get a theory that somehow has a geometrical realization of this group, right? Which is, we know that if it is infinite dimensional, then you might imagine that if you have a theory where you can actually see how this infinite dimensional group acts linearly, it might give you some information of some kind about the theory that you won't see in other formulations. And also, we saw that there's recent work by Strominger collaborators that there's an abelian subgroup here of supertranslations, which has been linked, well, shown to be equivalent in some sense, to Weinberg's soft theorem. So the way of seeing is that, well, once we have this theory, can we actually see that how the action of this BMS corresponds, how the action of the supertranslations corresponds to soft theorems of these amplitudes, right? Of course, first, before we have to get a model that actually calculates these amplitudes in some sense, without having to go through the book. And I'm going to show that that's another thing that it does. It calculates the S matrix only in Scry, so inside Scry. Tree-level. So this tree-level S matrix inside Scry.
So I didn't get you said it calculates this?
It calculates, yes. Well, the model. It calculates, so the model. And of course, I'm going to expand on all these points, but it's just a little bit of, because it gets a little bit technical, so try to get an eye, and if you glaze over during the middle of the talk, at least, this is where I'm trying to get at some point. This is to get some model which knows about Scry. It's defined, in some sense, intrinsically on Scry. I wanted to have some form of action of this symmetry group that I can actually calculate with that. And of course, in order to see that, I needed to somehow, it has to be able to calculate this tree-level amplitudes, right? So that's where we want to get at. And that's where we actually got that, right? At least for two very, very, now very studied theories and very symmetric theories, n equals 8 supergravity and n equals 4 super EMUs. If there's questions at any point, just stop me and ask, please. Okay? So there's a little bit of setting the playing field here. So we'll start with Scry. What is the topology of Scry? Scry plus and Scry minus are really topologically just R cross S2 in 4 dimensions. So I'm just setting for now. Well, for all this talk, it's just only 4 dimensions that I'm interested in now. It has a degenerate metric, which is pulled back from a conformal rescaling of the target space metric. So it's really a null surface. And it's a null surface defined with a metric, with a degenerate metric defined up to this conformal rescalings. And that's, you can think of that, because it's defined up to this conformal rescalings, that's one way of seeing that you're going to end up with a bigger symmetry group than with the whole space-time. By the way, that's all this analysis is very nicely done. All the papers, but I think especially nicely in Ashtekar's asymptotic quantization. Very nice. Okay, so really you can see Scry as being some line coordinates u, and then I have some sphere, and I have a sphere here on top on this line. Okay. But as usual, in these twistor constructions, what we want to look is really the complexification of Scry. So I'm going to complexify Scry. This is going to be topologically C, locally at least, C cross P1 cross P1. Or should I write CP1 cross CP1? Very explicitly. So is this complexification where R just goes into, so the U coordinate just goes into a complex U coordinate. and the sphere just goes into CP1 plus CP1. So I'm going to set up that I have just a coordinate u for the C factor, and I'm going to have two homogeneous coordinates for each of the CP1 factors. One homogeneous coordinate I'm going to call lambda alpha. This is lambda 0, lambda 1. The other one is going to be lambda tilde alpha dot, which is going to be a lambda tilde naught, lambda 1 tilde. So I have too many coordinates here for this space, which is a three-dimensional complex manifold. So there is an equivalence relation here where I'm going to consider this complex coordinate up to complex rescaling. So u lambda tilde are defined up to a rescaling by r tilde u, r lambda tilde, where r and r tilde are non-zero complex numbers. So there's a projectivization of this space, and you see, by some reasons I'm not going to get into now, U has charge, ends up having charge U11 under this rescaling, right? So you can see scry really, I said locally, this scry is really then, complexification of scry, is really then this bundle, this O11 bundle. Is the total space of this O11 bundle over CP1 plus CP1. Of course, you can not. This is not. Well, you can just think about this complex coordinates if you wish. If you wish to be more down to earth. Okay. Questions so far? You can go back to Lorentz signature, but just by looking at the slice, the real slice given by this. And then you have to glue these two guys, and probably just alpha 2. This brings you back to real Lorentz. Okay? So this is going to be the target space for the method. So you imagine that what actually happened is that there is this complexification gives you, or comes about from some identification between scry minus and scry plus, because I'm not going to be talking about scry minus and scry plus as separated, but only about this complex, this complexification of scry. Okay?
Your intuition is that scry plus together with scry minus should be thought of as this complexification?
Yes, that's the intuition. It's really that you should be able by, if you think about it, thinking about the amplitude as analytic, it's going to be an analytic function on scry, and so by doing time reversals and just moving around, they can go from one to the other through the complex. They can go from something with that is incoming to outgoing, or other way around, by just doing an analytic continuation. So I'm thinking that I'm gluing them in this way. That's the intuition. Okay. Okay. So this complex space now gets, there's an action of the symmetry group, so the BMS group also acts on this space. And so now I'm going to be more precise. The BMS is split up into a semi-direct product of two factors, supertranslations plus Lorentz rotations. Now this is the real group, but this SL2C becomes an SL2C on the two factors of the sphere, and the supertranslations, I mean, the way that they act is by sending the coordinate u 2u plus some function of lambda and lambda children. That's all they do. So the complexification of this is straightforward. You only need that alpha has weight 1 on lambda children. And you see here now that this forms an abelian subgroup, infinite dimensional, because this is any function on the sphere. And even more is that if you expand alpha into spherical harmonics, you find that L equals naught and 1 corresponds to Poincaré translations. And the rest corresponds to, they are not necessarily, well, it corresponds to more general translations, like sphere-dependent translations. Okay. Now, the work of Barnack and Tressert was, well, you can motivate by looking, well, we have an SL2C, so there is a sphere somewhere, and you know there's a sphere because topologically it's R cross S2 in the real. So, well, can we define a symmetry algebra then, where I have super translations cross Virasoro? So I don't require this to be global, this conformal transformations to be global in the sphere, I just require them, I mean, where I allow them to have some poles somewhere, right? And which is called an extended BMS algebra by them. And you can do that. There's some slight issues with charges because naively they diverge because of the poles of this, but you can do that. But you can, at the level of the algebra, study what this is. And really, exactly what you're doing is just, instead of considering global conformal transformations, just consider local conformal transformations. And the interesting thing is that there's been some work showing, relating this group, or these symmetries, to subleading soft theorems. And we're going to show now is that the model will also have an action of this algebra, and we can also recover the subleading term out of the action of that algebra. Right? Good.
Do you have two SL2Cs acting separately?
Yeah. So in the complex, you have two SL2Cs that are acting separately, one on the lambda and on the lambda children. And it's going to be very apparent because the generators are going to pick at the end. You're going to see that they are chiral segments. Okay. Just one more thing I want to talk about here on Scry. So on Scry, how do I encode relative data? Well, there's quite a lot of work that I'm going to condense in just 2 lines. That relative data is encoded in functions, well, with weights. So, for example, I have my asymptotic shear, which is a function of u lambda tilde. This has weight -3, 1. And there is a function called the Bondi-News function, which is also a function, well, it's a section of a line bundle, which is defined by sigma, so it's the u time differential derivative of the asymptotic shear. And this, just by discounting, has weight -4 and 0. Right? There is, of course, another one, which is the other helicity, if you wish, with weight 0 and -4. And this is the relevant for gravity scattering. This introducing now because it will come up shortly again. And you also have something similar for Young-Mills, where you have a gauge field, asymptotic component of a gauge field, which has weight -1, 1. and you do basically the same procedure, you have a function which is in some sense the time derivative of this asymptotic gauge field, which has weight minus 2 and 0. And this is called the broadcasting function. So this is the news function. This is the broadcasting function. So those are the things that encode radiative data. And
BMS symmetry is relevant in the context of animals.
there is a generalization of that where, as Sabrina was saying this morning, you let the gauge transformations, they don't go to constant, they go to allow them to depend on the sphere.
Mm-hmm.
In the same way that the super translations depend on coordinates on the sphere, you let this gauge symmetry depend on coordinates on the spheres. And yeah, and then you have.
But is it generalization or it's a different story? You forget about BMS for the case of humans and you develop a story for gauge transformations?
You can develop a story for gauge transformations. I don't know which. I mean, they are gauge, but they're not really gauge in a sense. But yeah, you can develop a similar story with all these follow-up conditions and everything for EMUs.
But it's not that you're considering BMS together with gauge transformations.
Well, since I'm going to be doing n equals 4, well, there are some U1s there, so I do have some gauge fields. I have some spin 1s on the multiplier of n equals 8. So, but I'm not going to be talking about them separately from the graviton. There's a paper with him where I do only for the n equals 4, and then I talk about them. We talk about them in more detail. But there's actually not much difference between them. It's basically the story goes more or less the same. But if you want me to, at any time, write formulas for the gauge theory, I have them. Okay, so there's only a couple more things to set up. So I was talking about the external data, right? Which are these functions, or I can do the Fourier transform of these functions and consider them in the momentum representation. And I want to be talking about massless scattering, so I'm going to be talking about momenta, which is massless. So I'm going to use for the external momenta this representation where I have an energy, lambda, and lambda tilde. So this is really the Fourier transform. Fourier transform of U. So it's just the energy, and this is really a point on the sphere somewhere where this momenta is pointing. Right?
How are spinor normalized? To write this, you need to know.
They are not normalized. They are so that's
Okay.
these are is defined up the scaling again. So this is defined up the scaling. So but now I have of course the opposite scaling for W, and this is scaling for lambda, and this is scaling for lambda tilde. So there's this. Right. One thing that I just saying that what is nice thing about having this kind of twistor space or Scry descriptions is that you really do trade the spin by this scaling, right? As I'm trying to show here, you have for the graviton radiative data, for gravity radiative data, you have a scale -4 or 0 -4, while for the spin 1 you have -2, and this holds true for the other spectrum, for the scalars, for the fermions, it just goes through in this way, which is very, very nice way of encoding the spin. And the last thing is supersymmetry, which is, as usual, supersymmetry makes life easier when you're calculating this kind of thing.
Since you almost explained it, can you explain how, for example, a plane wave is translated into some data at Scry Plus?
I can write you very specifically how, I'm going to write later
Okay.
what a plane wave is. I can write it down. So a plane wave will have I. You can write as this times omega I tilde to some power. So the power here will really give the scaling, so it gives the spin. So for a graviton, that's what I want. Good. Then I'll have a delta 2. I'll in a moment explain this. It's just like this twistor wave functions. Each is a omega ti tilde I. So it's a plane wave on omega. So it's a plane wave along the. It's a plane wave along u. So it has a fixed frequency. And you're fixing its direction to lie along some specific, in a point on the sphere, right? So if you think about them this way. Well, now this slash force I'm going to just explain because that comes from the SUSY. So this actually represents a. I'm going to get to that in a second. So to supersymmetrize this, it's quite straightforward. You just look at this, the CP1 cross CP1 part of your manifold, and you adjoint some P fermionic parameters on each one. Right? So this gives n, which number of supersymmetries equals to 2p. And what I'm going to parameterize them is by a big lambda. I'm not going to change. Just going to change the index. This is the previous lambda alpha, and there is an eta, where this a goes from 1 to p, and same thing for the tilde one. Lambda tilde alpha. And eta down, tilde, and this has the same range. Okay, and
you say again what's written in the exponent of that?
This here,
yeah,
I can do it a bit later. So there is external W. There's this factors that fixes the weight. Two TIs, TI tilde, and then there's, here I'm writing as a worksheet field, but this is the coordinate U on the target space. Yeah, so this is external, and I'm fixing them to be some point on the target space sphere. Of course, this in some senses is like a residual integral in the same sense of this other twistor, in this twistor space expressions usually are.
Are there any space-time coordinates here? Or where is the plane wave?
So the space-time coordinates, well, that's the square coordinates that really are the fields. So this is the coordinate on the CP1, or CP1 slash P, and this is the coordinate on the CP1, the other CP1 slash P, and this is the coordinate on the C factor. So these are the coordinates, coordinate. This is an external, so these guys are all external. So this is the omega I, lambda tilde I. So this forms my external momenta pi.
Where is x? Yeah. If it's e to the ikx?
There's no x.
There's no x.
I mean, the target space is a scry. I'm mapping this into scry. I don't want to talk about the bulk, I only want to talk about the asymptotic boundary.
So this is just for the expansion on scry?
Yeah, it is a plane wave on scry, it's just translating the plane wave into scry.
Okay. It might also be helpful to say if you pick a point x in the bulk, and you look at the future going like, then that will intersect scry in u equals x lambda tilde.
Please how to translate e to the ikx in bulk on the data on Scry? Does one ever need it, or maybe one?
You can. I mean,
But the point is that the delta function supports you on k.p equals 0. Actually, no, what I'm just saying there is good in twistors, but maybe not good in this.
I think it was the whole.
there's kind of a one-to-one map
Sorry, yeah.
between the two. So it's like if you wanted to write a plane wave in twistor space, you write some cohomology class, and there's no sign of x anywhere, right? But there's a prescription that tells you how to recover x. If you like, there's a way that if you could turn that object into a cohomology class on twistor space, and then perform the Penrose transform and read off, you would get something. So for instance, suppose you wanted to do a self-dual gluon, you would get a plane wave that had frequency omega, and its polarization would be proportional to lambda, or 2 lambdas, I guess.
Yeah, I mean in twistor space, you see, what you can say is that when p.k equals 0, k.x can be written in terms of the twistor coordinates. But in fact, what these guys are doing is something slightly different from that. So that's a statement that works when you're using twistor variables. But your model does have twistor variables, but that's not the way you express things in terms of the.
No, it's just Scry.
Yeah, that's right. Yeah, no, it is slightly different. Actually, I've always been slightly puzzled by the interaction with the Penrose transform here, because it always sort of like you're using H2s instead of H1s to me. Anyway, sorry, this is digression. Maybe I should let you go on with it.
But interesting.
But there's still some puzzling features here. I would
Sure.
say.
Let me just digest this formula.
Yes.
You integrate over theta, well, over 2 t's, the free data in your null momentum, and what is left? It's a function of what?
This one.
Yeah.
This is a function of omega i's, lambda i's, lambda I. And as an external data, and is also a function of u, lambda, and lambda as your target space. Right. The same way that a plane wave is a function of k, which is external data, and a function of x, which is your coordinates in space. This is a function of the coordinates in your space, and also has some external data that comes with it.
And where are they? The coordinates in your target space? Where are
It's
they?
this lambda.
This is good, okay.
This lambda, and this u. It's just that I have a sphere embedded, so you become a map in this sense. It's not really clear. Okay, and just finish this. It's just, as you might have guessed, p equals 4 gives you n equals h sugar, n equals h supergravity, and p equals 2 gives you n equals 4 supermeters. At the level, straightforward, the level of the supermutuplet, and then also the level in the interactions later on. You can just calculate the amplitudes. Okay. Questions? Because now this is the background to the model. It's a bit involved, but hopefully it's not bad. Okay, so I'm gonna turn this up. This down. Okay. Or mock-ups, because you can talk about gravity engaging kind of at the same time. So there is the main part of the action, which is this map from the worksheet into Scry. So I'm picking my two-dimensional worksheet and mapping them into the complexification of Scry. And so I have a field U for the U coordinates. I have a field lambda for one of the sphere coordinates. I have also a field lambda children for the other coordinate, for the other sphere coordinates. And this action on shell tells me the bar u, the bar lambda tilde is 0, tells me they are holomorphic. This map is holomorphic into scry. Right. Now this is the free action. Of course, I have to be careful because all these fields have scalings, and I want to gauge those scalings because it's just a redundancy. In particular, then I have to take care that I have two line bundles, L and L tilde of degrees d, and this one I'm going to call degree d lambda, d tilde. U then is just a function of the section of this line bundle. Lambda is also a section of this line bundle. Of course, it has some vector index here, which takes value in this space, and then has values on line bundle L because weight one here, and then this one. As values on L tilde. Weight one, right? These fields here have values on the cotangent, so this is actually, I can actually integrate this as a 1,1 form, and they have the exact scalings to compensate the scalings of these fields. Just the usual.
So it's a line bundle over what?
Right?
The line
That's a line bundle over the sphere. So this is some abstract CP1, and then these L's are line bundles over holomorphic line bundles over this sphere. So you can do the user of Faddeev Popov. I want to gauge those line bundles because my coordinates are only meaningful up to those rescalings, so I have to add some ghosts for this. There's an MN system of fermionic ghosts that is gauging the line bundle L, if you wish, and M tilde and tilde we're gauging the line bundle L tilde. So these are the what I'll call GL1 plus GL1 ghosts.
Sorry, this is just a
Yeah,
typo, but I think you mean CP1/P.
I do mean CP1 slash P. No, this guy. He has two
Oh,
indices
before, okay,
before
okay,
you're doing
okay,
it,
okay.
so he's CP2 slash. Yeah, they're projective coordinates.
No, actually, you mean C2/P then?
Oh, sorry, yeah, I mean C2. Yeah, that's right. Okay, now.
Yeah.
And my notes is actually C2. My only stupidity. Okay. I'm going to take those 3 degrees to be bigger than 0. Also, just so that gauging just implements the redundancy on the definition of those coordinates. And this is both. So these things are both present for the gauge theory action, for the gravity action. There are a few more things on this model. So if I'm talking about the gravity model, I need supersymmetry on the worksheet. So it's a model is very much similar to Dave's n equals 8 twistor string. So I have some fermions, and I'm just going to write them down. If you want to know more, you can ask me about these details later on. So I have these 2 fermions on the worksheet, plus this is matter. And then I have 2 sets of ghosts. And these are ghosts for Susie. So there's a worksheet Susie that is being gauged. And then there's another piece, which is some weird system, which I'm not going to talk very much if no one asks, but we can talk about this a bit later. Well, and then for the gauge theory, there's no such thing. It's a bit simpler. You only have a usual BC system. So this is the usual BC system from string theory. So gauging worksheet gravity, Cairo worksheet gravity, plus there is also a copy of this slightly weird system.
Sorry, Don. So what's W and U?
So W and U are, so W is really a section of the canonical bundle cross L minus, well, sorry, L tilde minus 1, right? V is a section of canonical bundle cross L, and V tilde is a section of the canonical bundle cross L tilde minus 1. So it doesn't have any weight you can integrate, and yeah, it doesn't have any scalings with the line bundles. That's what they are.
And as you already said, the important point is that U, lambda, and lambda tilde are just describing coordinates on the target, coordinates on the target, and everything else is just there to make sure you've got a holomorphic map.
Yeah, they're Lagrange multipliers if you wish. That's the way they are. Okay. So, question. So there's this. Okay, there's this GL1, and what you can see is that in both models are anomaly free. GL1 anomaly free. So anomaly free in this sense. Yes.
It's not clear to me why this is a gravity model and why this is a gauge model. So suppose you see what's wrong. You have the density charge and you see it from the cohomology and you see you have the right spectrum. Right. How do I read out?
The getaway answer question might get away from J03 cards is that this is what you do in Dave's model, and then equals 8 twistor string, and then you can play around and basically guess that that's what you need also in this system. Why is going to be a gravity model? I'm going to tell you right now about. Oh, I'm going to tell you part of the cohomology now, so you can see that there is actually something related to gravity in the cohomology of Q here, but yeah, it's simply not obvious that it is. That has to be a gravity model.
In fact, I'm confused why there's no BC ghost up there.
Yeah, we too. We are too. There's in a sense an effective BC ghost, which I can talk to you. You know, so this system here that I want.
They are maybe twisting the R as ghost.
In a sense. Well, I wrote here that these three independent line bundles. If I'm being honest, I don't think they are actually independent. There's some twist going on there, where here in this model, instead of gauging K, you're gauging L tilde, and you make an identification of this line bundle of the holomorphic cotangent bundle with K, and then in some sense gauging gravity. But we are really not sure about how that is happening. But if you want, we can talk about this a bit more later on, not when it's being recorded. Okay. Central charges are not zero, so the central charge for gravity is minus 20, while the central charge for the gauge theory is 0. So that's right, but it's also going to be thinking now at 3 levels, so it kind of doesn't matter for now. But just so you know. Okay, so my BRST operator basically what it's doing is implementing this GL1, and in the case of gravity, an extra symmetry, which is the supersymmetry, right? But what I want to fix now is this GL1 cross GL1. So if I look at the BRST cohomology of this operator, then I need to find, so physical operators have weight 0. (0,0). So, which means, so we're going to look at the simplest ones, which is then going to be some function of my matter fields. And I'm going to choose to look at this subset of physical operators. They have weight 0, and these guys have fermionic coordinates. So I'm going to do an expansion on those fermionic directions. And so this expansion starts with a field with weight 0. I have some stuff in the middle. I have 4 fermions, so the top part of this multiplet, where I'm going to have something of weight -4 and 0. Then a bit further, I have 4 eta tildes here and something of weight 0 minus 4. And then bottom of the multiplet with eta 4, eta as well, eta tilde to the 4th, and I have some other field with -4, -4. Okay? So this is suggestive because this is exactly the weight of the Niels function, and that's exactly where the graviton, the multiplet sits, the right-handed and the left-handed. So the two polarizations are sitting there in this multiplet. It's a bit weird because we start and finish this multiplet. Well, we start and finish with some scalars, and the fermions and gauge fields, everything else is in the middle. But that's the way that the supersymmetry runs in this case, because we really have split, because you did CP1 slash P, CP1 slash P, we had split the supersymmetry evenly between the both, left and right-handed, right? So you only have really SU4 across SU4 subgroup that is manifest on this description.
So manifest parity symmetry. So
Yeah, manifest parity symmetry.
you
You have
name
to
the scalar.
you have to change. Yeah, you have to pick something. Right. But you do have. But here is where the graviton, the gravitational relative mode sit, is on this Niels function here. And of course, you can do the same thing for where I have this was the p equals 4. You can do the same thing for the p equals 2. There's also again a function lambda lambda tilde, and you also start with some scalar, some 0 0 dot dot dot. Then you have the broadcasting functions for weight -2 and 0. There's an eta squared. There's an eta tilde squared f0 minus 2, and well done some other scale. So it's just the way that this multiplets go. But this is the way to see that just because of the supersymmetry that here you have the gravity multiplet, this doesn't have gravity, but it has the gauge fields sitting inside the physical vertex operators. Okay. So I have a few minutes, so just good. I can just not. I have to go into the calculational details. We all set. Have all the fields. We have this mapping to simplification of Scry. We have some DRST operator. We know part of the cohomology, and we can already see the relative modes of gravity and relative modes of gauge theory sitting inside these vertex operators. Right, so what is left to do is correlation functions. So I'm going to write down the expression, and it's going to have some things that I'm not going to explain unless you ask me later. But if you know string theory, those extra terms are easy to understand. So you have n insertions of the gravity vertex operators at some point sigma I. This guy is less standard. It is an effective, well, it acts as an effective B ghost, which is paired up with some Beltrami differentials. And then I have two sets of picture changing operators, just because I have this, I'm engaging the supersymmetry. I seem to have quite a lot of them because they are, they interact with the line bundles. They have values on these line bundles. So the number of zero modes really depends on the degree of the line bundles. But they are not important right now because all the magic happens here. And so because all the magic happens there, then I'm just gonna suppress those correlations, and I'm just gonna do the OP between those two. So I have, as you would expect, 3 fixed vertex operators, which don't change, and I have a set of integrated vertex operators, and I have n-3 of them. So then we come with this field chi, and so this dot is a U derivative. Because W is conjugated to U, there's a U derivative, which we just write this explicitly. Of CJ. And I'm suppressing all the other correlators. So the claim is that if you go and do all the correlations, and you're going to end up with an expression which is equivalent to the 3-level. So this gives me all the 3-level amplitudes. So this is a 3-level S matrix. For n equals 8 square gravity. But the formula is completely written in terms of scry. So I think Freddy, so the formula that you end up, if you massage it a bit, is equivalent to a formula that Freddy had. And then because Freddy massaged the formula that David had for n equals 8. And you can do the same thing with a very similar thing with a gauge theory, amplitudes. And what you find is a formula that is written only in terms of scry, and which you can show to be equivalent to Witten's formula for the twistor string. So, I mean, it seems, it doesn't seem like much, but actually, I mean, you've done all this calculation in terms of the worksheet, and the worksheet doesn't seem to know about the bulk, is how everything has been done in terms of scry. So that's quite interesting, that you don't have to go through the bulk to obtain these 3-level amplitudes. So that's the first of the things we wanted to show. It's here, although I'm not showing you explicitly, it's out there. You can also look at the paper. Now, I think people might be more interested is the target space symmetries. And I'm going to spend the last 5 minutes then quickly showing you how they act. So target space symmetries, well, it's easy to see that how to implement them using the CFT. So I had an SL2C I wrote in the beginning. You can implement that by having some constants, some matrix A alpha beta, and then I have these 2 fields, and this implements plus complex conjugated. This will implement the SL2C on the CFT. I can look at translations, and then this is going to be implemented by using a matrix, as you expect, just a vector, that's just a translation. Sigma dot times sigma. And the way to do this is by just doing OPs. This they are the usual OPs that U and W, for example, have OP 1 over Z minus W. And then you do a counter integral, and you get the answers. So we have those 2. And we wanted to look at super translations, and we can look at super translations. They're not more difficult to write down. You just write, so for the super translations, there is a generator that you can write down. Some function f for lambda tilde times W. And because W acts like this, there's this OP with U, then this W really acts as a derivative operator on things that depend on U, and multiplies by this field, which has weight 1, so it does implement super translations. Right? So very, very geometrically, very neatly, you can do this with super translations. And now if you throw that super translation inside this correlator, so I'm going to write this down. So look at what is the action of a super translation inside this. So I have my fields phi, and I have my fields phi. So what is this? Well, this is easy to compute. It's just a counter argument. You get the external energy of each particle times the function evaluated on each point on the sphere. Sigma I is lambda children of sigma I. Okay. Now, if I pick my f to be some specific combination of spinors, so it's true alpha and beta is just auxiliary spinors, lambda s represents what will be the soft momenta, if you wish, appears as a parameter. Yes, S stands for soft, so I have some soft momenta given by lambda s and the tilde s. And here I have the field dependence, sigma lambda b sigma, and lambda tilde alpha dot on sigma, and then the all important pole. There's a pole on lambda s. And as I promised before, this is chiral. This doesn't see the lambda tilde field. There is only a pole on the lambda. It's a simple pole, and you can just plug this in and evaluate with the counter arguments from before. And what you find is that this expression turns into omega I. Now using spinor helistic notations, angle brackets and square brackets, I and E over SI AS. Yes. And this is Weinberg's soft energy. So, just going back, we can define a charge for supertranslations. A specific supertranslation then acts inside my S matrix as just like a soft operator. So where S, lambda S and lambda tilde S play the role of the soft momentum. Right? This is the energy, and you can absorb this energy. Usually, it's absorbed in the scaling of one of these lambdas when you look at the space-time perspective. So that's the other thing we can find is just really this action, very nice action of the supertranslation group on the amplitude by just doing contour, just doing CFT tricks.
So it's slightly different from the way we did it in the sense that in our case, the supertranslation generator was the soft graviton.
Yeah, but in your case,
But in your case, that's not true then.
No. But what you can see is it's not, but it's close enough. So this function here has weight -3 and 1 in lambda s and lambda tilde s. So it looks like an asymptotic shear.
I see. So you can sort of see these.
So you can sort of see it over there, yes.
Yeah.
I mean, it doesn't come from expanding the vertex operator itself. The vertex operator is really has the News function there. But this looks like asymptotic shear in that sense. But it's not like your story. Your story is you have the vertex operator, you expand the vertex operator, and you get the soft terms. No, here we have a geometric.
It does look a bit different here, but it may be that on the supports of the delta, it depends on how you, it requires a sort of reinterpretation of the delta functions. You're reinterpreting as a,
Yeah, exactly.
so maybe you could do it for both of them. Yeah.
So, and just to finish off, we can also remember that we were talking about before of changing the SL to C. Maybe I should just level the algebra by the Virasoro, and you can do that here by considering these operators. there is a matrix depending on the fields. B plus complex conjugated. And if you look at a particular matrix, the children as A lambda sigma and children alpha dot. So, yeah, from the children dot S lambda children S beta dot over is the pole at the soft momentum, and then there's a normalization factor. So if you look at this and you play the same games, you find that this actually that has a Virasoro inside the algebra of those charges, and this gives the subleading soft term. So to summarize, here is a model. There's also very analogous story for gauge theory, which I don't have time to get into now. But you have these models which have a target space scry. They compute these amplitudes just from the boundary perspective, these reliable amplitudes, and they have a very nice geometric action of the symmetry of scry, BMS group in this case, and also of this extension, and you can just really go and compute by doing just simple CFT calculations. And that's it.
I have a question. Are scattering equations relevant here? Because this is, as you explained, this is about maps into null space.
Yes. So the scattering equations are, they're just like in the twistor string. They're hidden inside the vertex operators. So those delta functions, they are the scattering. They end up being the scattering equations. There's a grading by. There's also grading by degree when the degrees. The scattering equations get separated into the symmetry degrees. It's just that they look different because you're expressing them in terms of scribing.
So then the related question, is there any analogous story for the scalar field? We know that one can get scattering amplitudes for the scalar field.
Yeah, so
scattering equations. So how would you do scalar field here? Just this bijoint scalar.
Oh, the bijoint scalar. I was going to say the scalars are inside the multiplets.
Yeah. How would you do just the simple scalar?
I think you can do, but I have to think. I mean, I don't know off the top of my head how we'll do for scalars, but I don't know if you'll have a model that more or less makes sense, but I think you can come up with some correlation which you could do for scalars as well. Just because there are scalars here and it should work for scalars. I don't know, does the paper with Freddy have scalars? I don't really
Not
know.
that I know of, but
I'm sure it can.
I'm sure it can be
Yeah.
done. Yeah.
I mean, there are various people, some of them in this room, who understand, or at least claim to have understood how to go from the CHY formula in 4 dimensions to kind of spinor helicity type expressions one might get in a twistor framework. You could just take the CHY formula for the bijoint scalar and apply the same procedure. You'll wind up with a formula. This formula should be correct.
Yeah.
Given such a formula,
One can
it should be straightforward to cook something.
But also you can just do it in the sort of dimension-independent way that Violon code do.
Yeah, I'm just
Yeah,
feeling
yeah.
slightly confused about the. Yeah.
I think, well, I would have said it there, but my co-authors would agree. So
Yeah,
we
I'm
had
not
a
sure.
four-dimension specific formula that we knew very well, understood, and we could see that there was a very clear link here to Scry and to the Soth theorems and complex transformations. But Lionel and Arthur and Yvonne
Yeah.
did this in a dimension-independent way based on the sort of PX type ambitwist model. And I think the sort of insight that it brings is actually much better.
I think there's one important difference though here, which is that vertex operators in this model are explicitly given in terms of radiative degrees of freedom, not in terms of a graviton or a gauge field, say.
I mean,
Well,
there's a package.
I would
but
challenge
also-
you to explain that packaging story to us.
But it is different. The target spaces also ends up being.
I mean, I think
But this is more economic, right? This is half the dimension of the space that is used.
Well, no, it's not. They've got all the same variables. I mean,
Yeah.
in our, I mean,
No, because
we
this is-
just, I mean, I should say, flat out, we were just copying their idea, but just re-expressing it in the dimension independent model. I mean,
Because
we
there's-
absolutely relied on their
Let me
insights.
listen. This conjugate variable. This is the
Yeah, but I mean, they have conjugate variables as well all the way through. So they have u lambda lambda tilde. And you can actually
And they're
do
conjugate
you can
variables.
actually do a one-to-one correspondence. You can re-express theirs as an ambitwister model, but it also has lots of sort of slightly difficult to interpret ghost fields as well, which I've never properly understood.
In geometry, it works slightly different. But it's,
Yeah, but I think I don't see that the scalar model works in any different way to the vector or spin 2. But of course, with the memory effect, of course, it's very difficult to see that you could have that in the scalar case, whereas because it's all about gauge treatment. So that's something which must evaporate in the scalar case.
so. I'm puzzled about what any of this really means. In that, what nobody is quite brave enough to come out and say, but that everybody secretly thinks, is that you hope that these BMS transformations or some version of what might be like BMS transformation is some sort of clue as to a holographic description of theories in asymptotically flat spaces. And this is emphatically not that. Right? I mean, it might live
No.
in Scry, but the data involved is boundary values of gravitons or things like that, not some operators in some totally different theory that are dual in any sense to graviton. Even the fact that we had to complexify Scry to write this story down, in some ways, again, from a GR point of view, it's very natural, or at least done very often. From a non-perturbative, if you're really trying to compute a bulk gravitational S matrix in some sort of well-defined theory of quantum gravity in the bulk in terms of some totally different boundary theory, is it reasonable to expect that well-defined bulk quantum gravity will exist complexified? If not, how on earth do you want to squeeze all this information through a point of...
yeah, the complexification is really.
No, that's not too bad, because I think the idea is that certainly the gluing data. I mean, so we're talking here about sort of complex manifolds, and these in the ambitwister story they get to be quite large. I mean, if you think about what Eduardo was doing there, he was taking Scry, which is just a sphere cross R, and that sphere turns into CP1 cross CP1. You go all the way out, and there's no way you expect any of your data to extend from that real sphere to the big ones. And if it did, you'd have the Udall theorem telling you that the data was trivial. But what you're trying to do is you're trying to glue together a complex manifold, and you really interpret the stuff that lives on the real slice as some sort of gluing function. And then your strings, so to speak, you have got to thread through from one patch to the other patch through that real slice. And so I think that kind of concept of complexification sort of makes reasonable sense.
You said it in a much better way than me, but I'd still say that what you were just talking about was a classical or perturbative around classical description in the bulk.
No, but I don't see. Yes, okay. So, right. So
any honest holographic theory might well not, if such a thing exists.
yeah.
It's not clear you could expand it in that. Well, it's not really even clear what the expansion parameter is supposed to be. Right? There isn't a dimension. It's coupling. It would have to be some effective. This is very, very far from any holographic. I mean, it might be a step in the wrong direction. It was just a way of seeing how BMS or extended types of BMS transformations.
How do these ideas relate to asymptotic quantization ideas? Old asymptotic quantization.
Well, in many
How much-
ways, I mean, for me, that's the big surprise, because so the way that I like to interpret this was to say that these vertex operators are, in some sense, that they do have an interpretation as the the Hamiltonians that generate the scattering of null geodesics from scri minus to scri plus. And what this picture seems to do is to tell you that those Hamiltonians are in the string theory. They are the vertex operators for gravitons. So there does seem to be the string somehow gives you the correspondence between null geodesic scattering and gravitational scattering, and I guess the string is already in some sense giving you the correspondence the level of the sort of the way in which a string theory would set up a Hilbert space between those modes of the ambitwistor string and the gravitons themselves. So, yeah, the strings do provide quite a non-trivial relationship between null geodesics or complexified null geodesics or strings and ambitwistor space.
Why would I be led to string if I wanted to quantize structure of null infinity?
Good question. Yeah, I mean, no, but that's the mystery in all of string theory, isn't it? I mean, that's that. Yeah, string theory does happen to sort of work, and why on earth are you looking at modes on a string to, I would say, the string theory has been saying for 50 years. So you can encode a graviton in the mode on the string.
Yeah, but that's the CFT, it's the state operator correspondence.
Sorry?
That's the state operator correspondence. You exponentiate your state, it gives you the deformation of the action, which is just exponentiate your graviton, or you do the deformation of the action, and that you can interpret as the exponentiation of the vertex operator for a graviton, right, for a spin-Chur field.
I mean, these things are sort of like a Wilson line operator almost. A gravitational Wilson line, just taking the action of null geodesic in the background. Somehow you say that determines the graviton. That's it.
I mean, sorry, to say it the other way around. So Stronger, and especially Andy's paper with Freddie, stimulated lots of little papers. Extremely interesting, highly important, which showed how easily these come out of scattering equation type formulation of amplitudes or this, that, or the other. And this, in some sense, was just another one of those, but at a slightly deep level, in that it kind of explains why it all comes out of those formulas, in the sense that if it's specifically a model whose target space is scry, you see the action of the
symmetry is very
symmetries on the target space. They have natural standard interpretations as charges on the weld sheet, and it all just falls out. Don't claim any more than that.
Yeah.